Hello, and welcome to this vBrownbag session here at OpenStack, Liberty OpenStack meeting. My name is Christopher Liljenstolpe, and I'm with Project Calico. I want to talk to you a little bit about where sometimes less is more, and we're really going to be talking about networking and networking options in OpenStack. What we're currently doing wrong with virtual networks and how we break free from the complexity trap we're getting ourselves into. Yeah. Famous quote from Albert Einstein, everything should be made as simple as possible, but not simpler. In the networking world, especially in the networking vendor world, we tend to forget this. We tend to design for the 100% in this industry. If you remember, for those of you who are in networking, about 17 years ago, somebody came up with this thing called tag switching, which became MPLS. It was supposed to be a very simple, very easy way of doing networking at scale. The working group in the IETF is still existing 15 years later and has produced over 200 specifications, and I would challenge anyone who would say that MPLS is now, or still, a simple networking solution. We run the risk of doing the same thing in OpenStack. Maybe we should have listened to Einstein. And there's some quotes from the Register about a year ago about Neutron. And in the last OpenStack user survey of November 2014, the project that got pilloried the most was Neutron. 16% of the comments were pointed at Neutron, and mainly around complexity and operability and stability of Neutron. So maybe we've done something and made this a little more complex or tried to solve for all the possible solutions rather than trying to solve for the base case. And instead of me talking about it, so let's look at the onion. This is the basic OpenStack networking model. We got a bunch of vSwitches on a bunch of compute servers. We've got some purple VMs, some green VMs, and we've got some services, and these things want to talk to one another. So what do? We build this like the old enterprise data model. We say, okay, the purples are in one logical L2 segment, the greens are another logical L2 segment. If purple wants to talk to purple, if it's on the same server, it's just a local vSwitch. So that's one data path, just local Ethernet. If purple wants to talk to purple on another compute server, we encapsulate it in VXLAN or something along those lines. So that's data path number 2. If purple needs to talk to green, I mean, sometimes people may want to talk to each other in our cloud, we hope. That requires an encapsulation from purple into purple's routing process. Purple's routing process finds green's routing process, forwards the traffic to that, and gets re-encapsulated again and delivered to green where it gets de-encapsulated. So you can involve 3 or 4 servers for 2 VMs to talk to one another. You have multiple encapsulations, de-encapsulations, multiple state. This starts becoming interesting to troubleshoot. Somebody calls and says, hey, my VMs couldn't talk to each other at 3 o'clock in the morning yesterday. I can't troubleshoot that without knowing where they were in the infrastructure at 3 o'clock in the morning yesterday, because if they have moved in the meantime, the data path they're using now may not have been the data path back then. So what I basically now need to do is understand point in time where things were to try and figure out what was involved when I try and troubleshoot this. This does not pass Chris's 3 o'clock in the morning test, which is simply if I deploy something into my infrastructure as an architect and it breaks at 3 o'clock in the morning, are the people sitting knock watch at 3 o'clock in the morning going to be able to fix it, or are they going to have to call me? I don't like getting called at 3 o'clock in the morning. That's a 3 o'clock in the morning test. If it doesn't pass the test, it doesn't go into my network. Now, you need to get to the outside world. Well, I need to NAT you. So I now have another piece of state I have to maintain. Or you need to get to your old NAS or database server, something not in the cloud, something not virtualized. I have to on-ramp, off-ramp you. Yet more state, yet more complexity in the network. This is starting to become fairly complex with lots of layers. This is the onion we have built for ourselves. Layers are complexity. Violate the 3 o'clock in the morning rule. Listen to Albert. So, how did we get here? We're all smart. Why did we get here? Probably the case might be that we ask ourselves the wrong question. Instead of asking what our VMs actually need to do, we said, how do people do it today? And we want to replicate that so anything that they do today in an enterprise data center, no matter how corner casey, will still work. So let's go back and see what do we really need to do in a cloud environment. What are the virtual networking requirements? Workloads need to be able to communicate with one another. And things need to be able to talk to one another. You need to be able to talk to the outside world. IP, for those of you who haven't gotten the message yet, has one. There is no IPX. There is no, ATM anymore, etc. We handle IP. Everyone talks IP. What I need to do is get these IP packets between one another. And I need to enforce some kind of policy. I need to be able to say who is allowed to talk to who using what protocols in what kind of context. I don't need to create an L2 segment because I'm handling IP traffic. That's the way people think about instituting policy. Policy can be used to enforce things like tenant isolation or other kinds of policies. It's a general case. I don't have a special requirement for tenant isolation. I have a requirement to institute a policy. If one of those policies is to provide tenant isolation, that's fine and reasonable and sensical. So, if those are my base cases, and I go to an internet backbone guy, someone who's built networks at scale before, you start wondering, maybe there's a different way of doing this. What if we built our data center like the internet? So this is the internet. I have a bunch of hosts with applications on them and IP stacks. They connect to routers fairly close to the edge. They could be a CMTS if you're a cable operator, or a PE router if I'm providing connectivity to businesses, or a DSLAM, BRAS, etc. So all of these things are routed. And then they connect over some kind of IP transport fabric. Could be L2, could be L3, could be carrier pigeon. By the way, there's an ongoing bounty. If anyone gets Project Calico running over avian carrier, I will take them out for a very nice dinner somewhere. So keep that in mind, everyone. And then over that fabric, I talk to other routers. In this model, the traffic is IP over Ethernet. Just straight up IP over Ethernet. No uncap, no anything else. So why don't we build the data center the same way? We now have VMs. They have applications and IP endpoints. They have IP addresses that are globally routed through a router that sits in each compute server. So every compute server has a router, and it routes using BGP and tells everyone else in the fabric and everyone else, all the other routers and everything else, where all these workloads are at any given point in time. This is Project Calico. We use open standards and open source code. From an open standard standpoint, we use BGP. We know BGP scales to millions of routes. We know this already works. So why not use the same thing in the data center where I could have potentially millions of containers? It's the only thing we know that scales at that rate. We program the routes into the Linux kernel on each host and into the physical fabric if required using BGP. All forwarding's done at IP. The first hop and last hop of every packet in Calico goes through the local router. I can apply ACLs and policy, as we're talking about, to provide tenant isolation or any other policy I want to. It's all natively IP. There is no vSwitch. And by the way, for you OpenStackers who want to do IPv6, Calico supports IPv6 natively today. Actually, it did from day one. So we actually have a fully functional IPv6 story in OpenStack. It's still a problem for some of the other solutions. How do we support this? We have a couple of components that get installed on each compute server. A BGP client runs in user space, and a client we call Felix, which is our actor in that compute server. Felix, as VMs come and go, Felix programs routes into the routing table on the Linux kernel, and configures the security policies as ACLs also in the Linux kernel in the compute server. We're using the Linux kernel as routing. In order to find out that VMs are coming and going or policies are changing, we have a plugin that plugs into any orchestrator. Right now we plug into Neutron, we plug into Docker. We're working on other container plugins as well. And it takes that and puts that over etcd to talk to Felix so Felix can do the programming. BGP picks up the route updates, announces them to the outside world. Where are we today? OpenStack, Chef, Juju, in trials, multiple integrations with multiple packagers. Docker and Fuel is available for lab evaluation, and we have more integrations in progress. We scale, instead of having lots of state, we scale to potentially millions of workloads. It's easy to troubleshoot. Ping and traceroute are your friends. There is no on-ramps and off-ramps. It's all just routed. There's no NAT. You want a container to be exposed or a VM to be exposed to the public internet? Give it a public address. We can use ECMP and Anycast to provide HA and scaling. Basic IP networking is the only knowledge that's required to run and troubleshoot this network. How do you get involved? ProjectCalico.org. There's the GitHub, mailing lists. Download it, try it out. Let us know what you think. Project's available to be done today on OpenStack. It installs, we just did an install at a potential customer, 1 hour to get a networking stack up and running on an OpenStack installation. Up and running, passing traffic, 1 hour from start to finish. It's simple, it works, it's easy to understand. Thank you for your time.